Thanks everybody. Yeah, so I'm Randy Shoup, and I want to talk today about large-scale architecture, the unreasonable effectiveness of simplicity. And the genesis of this talk is really the idea that almost all the practices that we do in terms of technology and architecture and software delivery at large scale is all about simplicity. How can we make the simplest components, the simplest interactions between components, and the simplest changes when we change those components? And as I promised in the abstract, I'll give you a bunch of examples from eBay and Google and Walmart and a bunch of places. So yeah, super quickly, I've been a senior engineering leader at a bunch of different places, including eBay and Google and Stitch Fix and WeWork. And then actually last week I started as head of engineering at a smaller company called Thrive Market, which is an online organic grocery around the United States. So super excited about that. I thought I would start with a few architecture evolution stories to kind of set the stage, and then we'll talk about simplicity using some of those examples. So eBay started almost 30 years ago now, it's hard to believe. But eBay, depending on how you count, has gone through about 5 iterations of its architecture in those 30 years. So in 1995, it started famously as the founder, Piero Midyar, in a 3-day Labor Day weekend, playing around with this new cool thing called the World Wide Web. And he built this kind of toy thing that ultimately became eBay. But it was monolithic Perl. Every item was a file. I'm just imagining it like it was on some 386 tower under his desk, you know. So it wasn't something that scaled, but it wasn't meant to be. It was just something fun playing around, just like Eric Evans in the keynote, you know, playing around with LLMs. The next iteration was, you know, very cleverly called V2. And it was a monolithic C++ ISAPI DLL. It grew over time to, at its worst, 3.4 million lines of code in that single DLL. They were hitting compiler limits on the number of methods per class, so I'm ashamed to say that at that time the Microsoft compiler could handle 16,000 or 16K methods per class, and they were actually hitting that limit. If you've been in a monolith, like this one was pretty unpleasant. They weren't just in this, you know, it's not like all the 1,000 developers were in the same repo. It's not just that they were in the same file, they were actually in the same class. So pretty brutal. eBay survived though, and they ended up doing a migration to, again, what they cleverly named V3. So that was Java, a move to Java. So I don't want to call it microservices because it super was not microservices at the time, but you could call them mini applications, and a bunch of different applications, 220 of them at its largest. You know, one set of application servers for, you know, search, and another for selling, and another for buying and checkout and purchase and billing, et cetera, et cetera. And then all over a sea of shared databases. And then in 2012, they went to sort of their V4, that we could legitimately call microservices, and then there was another iteration of the architecture starting in 2017. So you can see this kind of, you know, evolution over time. Amazon has gone through a really similar evolution. It started almost the same time, again, the beginning of the web. People may be familiar with the original Amazon application, which was called Obidos. It was a monolithic Perl and Mason front end over a C language backend. It was a 4 GB application that lived inside a 4 GB address space. So like, that was uncomfortable. Lots of virtual memory swapping. They were regularly breaking the GNU linker, just simply trying to link and build the application. And it was so, I'll call it, effective at consuming memory that they ended up having to restart every 100 to 200 requests because they were accumulating memory leaks. And as a consequence, because again, it was all the people in Amazon in this same monolith, they were only able to release new code once every quarter. So that was unpleasant. But one of the great evidences of Jeff Bezos's brilliance, which I don't think is celebrated as much as it should be, is he tasked the whole company for the next 4 years between 2001 and 2005 to essentially break down that monolith into what we would now call microservices, build services in modern languages of the time, in C++, in Java, et cetera. And then the stricture, which really worked well for Amazon, and I think is a good best practice for the industry, is no shared databases. So an individual service owned its own data, and nobody could have access, backdoor access to that data from anywhere other than the published service interface. And I think it's interesting and instructive that basically the year after they finished this migration, they were able to start AWS and start their rollout of taking over, a lot of the world's technology infrastructure, but also, if you're a retailer, taking over a lot of the world's online retail. So if anybody ever says to you that architecture doesn't matter, I think both of these stories, but to be honest, particularly the Amazon story, really indicates how important architecture and architectural principles are to the success of the business. The obvious lesson to learn here is, and I think this is a good mantra, nobody starts with microservices, but past a certain scale, almost everybody's going to end up with something that looks a lot like microservices. So I wanted to structure the talk in these 4 different sections. So again, the idea is like all the things that we do at large scale are about simplicity. So I want to first talk about simple components, then I want to talk about simple interactions between the components, I want to talk about simple changes that we make to the software over time, and then finally I want to put it all together with some architectural ideas and then some particular examples about architecture examples that do these things really well. So let's start talking about simple components. And I'm going to have a quote, an inspirational quote in each of these sections. So I love this quote from Tony Hoare, which is, there are 2 methods in software design. One is to make your program so simple that there are obviously no errors. The other is to make it so complicated that there are no obvious errors. So I think we want to be in the first category rather than the second category. Obviously, that's what Hoare wants us to do. But yeah, so when we think about our components, how can we make those components so simple that there are obviously no errors in them? And the first idea, familiar to everybody here in the room, is modular services. We want to build large-scale systems out of small, independently developable and deployable individual service components. And certainly from a DDD perspective, we want to make sure that those service boundaries are matching the problem domain and represent a bounded context in our overall domain model. And those boundaries, as I was mentioning earlier, want to encapsulate both business logic and the data. So we want to make sure that all the interactions to that service are through the published service interface, that that interface hides any internal implementation details. I shouldn't be able to find out from the outside what programming language you use, what framework you use. I certainly shouldn't be able to know what database you use or even get access to your data. So absolutely no backdoors. And that's something, again, that Amazon put in relatively early in our evolution as an industry, but I think really showed the importance of that going forward. And it's also important to remember that these service boundaries that we have are also encapsulating a bunch of other important architectural ideas. So they encompass, they're a fault isolation boundary, they're a performance optimization boundary. So again, if no one can get access to my data, I can make improvements in terms of caching and query optimization and all sorts of stuff underneath, change data stores without your knowledge from the outside. And then also super critically in 2024, it's a security boundary. So the more that we can bound things like, hey, let's put all the payments stuff in one service or a collection of set of services and have that be in PCI scope and SOC scope, et cetera, as opposed to the whole system. Yeah, so it's a security and a compliance boundary as well. So once we're within one of those services, we want to make sure that the domain logic that we're implementing is orthogonal to the other ancillary parts of the system. So ideally, in a kind of functional programming way, we'd like our domain logic to be a stateless pure function if we can do that. And one of the reasons why we want to do that is it actually ends up, in my experience, matching the domain problem as directly as possible. Let's take all the inputs, let's process them as a pure function, and then produce the outputs that we need to produce, whether those are events or other actions that need to happen in our system. And if we do that, what I have found is that those aspects of business logic are very testable. They're very deterministic, and they're very testable by themselves, and they're also, interestingly, really robust to change over time, change in requirements, and certainly change in the technology approaches that we have. So I like to think about, when I'm inside a service, how can I do things in a straight line, just straightforward, within that service, very synchronous, minimal branching, super clean, super simple. And then, of course, we want to make sure that we're separating that domain logic, that pure function that implements our business logic, from any of the I/O things that we need to do, right? So, this is hexagonal architecture or ports and adapters, right? This is, let's keep our domain logic very simple and isolated, and then the things that interact with other systems and outside of the system are kind of ancillary and on the outsides of that hexagon. And the other way, if you come from the functional programming side of the world, like the other way to think about this is functional core and imperative shell. Cool. So now when we're in the service, we need to manage data, right? So typically a service manages state. So one of the other simplicities that we want to attack here, once we've bounded the domain with a service, is we often have to shard the data. Maybe we can't fit all the data for a particular thing in one memory. One memory location, or one instance of the service. So we want to. So often we'll divide those into shards. We'll divide those into like sets of data that can be operated independently. And those at these large-scale systems are often units for distribution. They're units for replication, right? We'll replicate those shards multiple times. They're units for separate processing and separate storage, typically. And it's super important that we hide those as an internal implementation detail of the service. Those shards are also units that encapsulate a bunch of important architectural properties, right? So they encapsulate resource isolation, they encapsulate a lot of fault isolation, particularly like infrastructure and hardware faults, they encapsulate availability, and they can encapsulate performance. And we're lucky in 2024 to live in a world where we often don't have to build those sharding systems ourselves. 20 years ago when I first joined eBay, we had to build our own sharding system. Now that's typically taken care of by any of the data services that you commonly use in the cloud. And those things those things in those well-written systems will auto-scale, right? So as our data grows, or as the processing needs on that data grow, we'll divide or scale out or those shards. And examples from those data systems are like DynamoDB does this, and Aurora and Bigtable. All the big systems are going to do this kind of sharding for you. So now let's pop out of the individual service and talk about the services as a collection. And the way I usually I call this service layering, but I know that layering has a really bad word in DDD. So I actually tried to describe what I think is actually the correct topology, which is thinking about services as a graph, right? Like the service at the top is talking to a graph of other services that are kind of conceptually beneath them in the system. And so over time, what you'll see at like an eBay or an Amazon or a Google or a Netflix is that services that are visible to customers are going to be calling other services, which in turn call other services. And it's not really a strict layering; it's really more of a graph. And why do we do this? Well, one is separation of concerns, but why does separation of concerns matter? It's because it really simplifies the job of any individual service team. So as a service team, we're going to be concentrating on the business logic and the particular things we need to do for our service, and we can abstract away the details of the dependent services that we have, and it allows us to focus just on the services that we are serving and the services that we are consuming. And when I led the engineering for App Engine, Google App Engine at Google, a lot of people would ask me like, how can you live in Google? It's like thousands and thousands of services. But yeah, most of them I don't have to deal with, right? Like I'm calling a small, single-digit number of services to get our job done, and I'm being called from, maybe tens of other services that are calling me. So it actually bounds the problem really tightly in a way that makes it a lot easier for the service teams to like keep their sanity. And then the other common thing at large scale is to have a common platform that underlies all of the stuff that gets built. And so the nice phrase that I think comes out of Netflix is talking about a paved road. So that's shared infrastructure, that's standard frameworks that are easy to use and are maintained typically by common teams. That's common improvements in the developer experience. And then again, that's helping the teams maintain separation of concerns. So the individual service team that's building their own logic and managing their own domain has their cognitive load reduced because the shared service teams are managing a bunch of the platform things. And actually, interestingly, one of the reasons why it bounds cognitive load is it reduces the number of decisions I have to make. Does that make sense? I see people nodding, yeah. Just simply by, here is the one way, or the two ways of storing data or interacting between services or whatever. It often doesn't matter what choices we make, but it is important that we make a small number of standard choices overall at the company. That actually makes things work a lot more smoothly. So as it might be counterintuitive, but in my experience, really organizations at large scale, at the eBay and Google scale, actually end up investing more than 50% of their engineering effort in what you would call from the outside platform capabilities. And the reason is, as you grow larger in scale, there is a super linear value in the investment that you make in the common stuff. Does it make sense? Like if I make an investment in the common part of the platform and I have 10 teams, okay, I get some set of value. But if I have 100 teams or 500 teams or 1,000 teams, like I can make a similar set of investment or a reasonably similar set of investment to that platform, but I actually get more of the value. So that's why the investment in engineering effort tends to be skewed toward the platform in the large scale. And then, so the service ecosystem overall is going to look like this. There are a bunch of external customer-facing services. There's a graph of other services that aren't directly customer accessible, but are maybe several layers of supporting stuff. And then there's underneath that a set of platforms that support the whole thing. And then there also is typically on the side a bunch of orthogonal cross-cutting concerns like security and the deployment system and all that kind of stuff. The last thing I'll say about service evolution is that it really is an evolution. So at large scale, it's a lot like a biological ecosystem. So there are constantly new services being created and services being retired. And in almost a Darwinian way, although I'm maybe overstating it, services only justify their continued existence by continuing to be used. And once a service is no longer being used or no longer being used very much, we will repurpose that team into the next iteration of that thing typically. Those services, individual services, are growing and evolving over time. And just like in domains, like you'll start out with a domain that, payments, and then like you'll subdivide and subdivide and subdivide. So it's very much like cellular mitosis that we learned about in high school biology, right? So we start with one thing, and then the teams and the services and the domains kind of cleave into smaller ones and cleave into smaller ones. And there's so much, I don't want to call it churn, but there's so much evolution in the ecosystem at Google that there's a little like Google saying with a smile on your face. It seems like every service at Google is either deprecated or not ready yet. Okay, so that was simple components. Now I want to talk about simple interactions between those components. And I love this quote from Albert Einstein: "Everything should be made as simple as possible, but not simpler." And that I think is going to inform some of the architectural ideas about interacting between components. At large scale, I think one of the most powerful tools we have in our toolbox is having that communication between components be an event-driven model. There's nothing really, well, I was going to say there's nothing wrong with synchronous stuff. Synchronous is always an option for us, but at large scale, it tends to work a lot better when things are event-driven. So we're communicating state changes between components in the system as a stream of events, and as we all well know, an event is just a statement that something interesting occurred, and if we do our modeling job well, that state change event represents something that's interesting, a kind of semantic domain event. And why do we do this? Again, it's to make our lives simpler. Again, simplicity is the theme here. It helps us to decouple the domains and teams. So we've abstracted that intercommunication as an event with its own schema, so it has a well-defined interface, and it allows the producer of the event and the consumer of the event to be asynchronous from each other. And it actually, in my experience, really simplifies the implementation that we make of the components, right? If all my job as a service is to take one or several sets of events, do some processing on them, and then produce one or several sets of events, that's a really simple and very, very powerful model. So now when we're within the service, one of the great ways to retain state is to retain state as an immutable log, and people will be familiar with this from event sourcing. And interestingly, while it can seem a little bit counterintuitive to people when they're first kind of introduced to the ideas of event sourcing and immutable logs, it actually often matches the domain really carefully or really closely. I'll give an example in the next slide. And again, as an architectural tool, the immutable log encapsulates a bunch of really important architectural ideas. It encapsulates durability. It encapsulates traceability and auditability. Like if we have a list of or a log of what we've done, it's pretty easy to go back and try to figure out what things went wrong. It allows us potentially to replay those logs over time. So when we make a mistake and we change the code or change how things work, we can replay that log and replay those events. And also, again, very importantly, being able to look at the log is very explicit. It's very easy to understand what's happened if you can look at a permanent log and have that not be separate from the processing that your system does, but it is exactly the processing that your system does. And then of course, since we're accumulating, if we do an immutable log, immutable means it never changes, so we're accumulating things all the time. So obviously the standard technique is that we compact those log events over time into snapshots. So the example, so Stitch Fix, people may know, is a online clothing business, and the details aren't super important, but it's a physical business that ships clothes to its customers. And so one of the things that was super important from our modeling of the domain very early on at Stitch Fix was modeling all aspects of picking and packing the box all the way through to shipping as an immutable log of events. So the detail, when we call one of those boxes a fix, that's kind of the name in Stitch Fix. That's where the name comes from. So one of those boxes goes through, the client requests it, and then we assign that box to be shipped from a particular warehouse. That particular box gets styled by a stylist, like the stylist chooses the clothes for the person. We style it, we pick it, we pack it, we ship it. It travels as atoms, through the world, and then the customer receives it. And this, I can tell you, just having the explicitness of this immutable log was hugely valuable when we had issues in the warehouses or issues in the earlier process or the shipping process. Super helpful. So the last idea I want to offer here is a really explicit plug for asynchrony between the components. And again, this is enabled by thinking about things as event-driven. But if component A and component B talk in an asynchronous way, it allows us to decouple those operations in time. So I like to say we decouple the availability of A and B, right? So A can be processing and producing events. B doesn't necessarily need to be up at that moment consuming the events. B can catch up later. And conversely, even if A is down and not producing events, B is still able to be consuming those events that have been produced before and continue to do B's work. So it allows us to independently scale A and B. They don't have to be scaled, in lockstep as we would have to do if that interaction were synchronous. In my experience, it allows us to do a lot more complex processing by giving us an easy way to do stuff in the background, essentially, so that the user is, requesting a box of clothing or bidding on an item at eBay or trying to book a room in a WeWork, something like that, and we can get back very quickly to the user in the matter of small number of milliseconds. But there might be a lot more complex auditing and checking and processing that we can do, and we do that asynchronously. And again, because we haven't coupled them synchronously, it's actually a lot safer from a systems perspective to make independent changes to A and B. And as with so many of these other techniques, it really simplifies our implementation of the component or the service that we're working on. One of the techniques that this allows us to do, which I'm going to discuss a lot later in the examples at the end here, is it allows us to take what originally might have been a synchronous graph of A calls B, calls C, calls D, calls E, calls F, and invert that, where instead of A calling when it needs to know the answer to something and having all those synchronous calls chunk have to happen in small number of milliseconds, if we invert that flow and we do it more event-driven, when when things about F change, it can produce events that are consumed by E, and it can produce events that are consumed by D to C to B to A. So it actually, I'll give a specific example later if this isn't clear, but by giving us the architectural flexibility to invert that flow to make it an asynchronous, almost data flow, as opposed to a synchronous call graph, it actually can be orders of magnitude, multiple orders of magnitude faster for the retrieval side, and multiple orders of magnitude less resource intensive. Because we're not doing everything all at once, we're doing things only when they change, essentially. I'll give a specific example from Walmart later, which is really, really exciting. Okay, so now I want to talk, we talked about simple components and simple interactions. Now I want to talk about simple changes that we make to the system. And the quote here that I really like is Gall's law. So a complex system that works is inevitably found to have evolved from a simple system that worked. And there's a converse that says, if you have a complex system that doesn't work, you almost have to start over. So I want to talk about like how we make changes at large scale to the system, and these techniques are going to be familiar to all of us. So every time we want to make a big change to the system, we want to think about how can we make that big change in a number of smaller changes, right? So we want to migrate from X data store to Y data store. We want to add some large set of new capabilities. Always we should be thinking, how can we take that large change and make it into smaller incremental steps that are easy to move forward and move back on? And so each one of those steps at large scale, we need to make sure maintains both backward and forward compatibility of both data and interfaces. So that actually really makes it important for us to make those changes really small. And as a consequence, particularly at a large service ecosystem, if you stop the world and look at the system at any given point in time, it is the common case, rather than the exceptional case, that there are multiple versions of services out there in the wild taking traffic at any given moment, right? So if you stop the world at Google, or stop the world at eBay, or stop the world at Netflix, and just look at the versions of the XYZ service, you'll see this one has version 16 and 17, and this one has versions 23 and 24, and this one is version 1.1 and 1.2. It's super common, and it's actually the common case to be in this transitional state of I'm migrating from version X to version N to version N plus 1. So how do we make that happen? We test a lot, and part of building our software is making sure that we test it. And from the perspective of like simplicity and providing value to our customers, the reason why we're not paid to do tests, but we're paid to produce high quality software. And in order for us to produce high quality software, we need to do those tests in order to help us go faster. So the metaphor that I like to use with skeptical, not engineers, is tests are the solid ground beneath our feet. So if we were running, do we think that and I'm a runner, so I will tell you that it's a lot faster to run on solid ground than it is to run on like sand on the beach. Like anybody who's done that, like it is really hard to run on sand. So it's much easier to run on something that's really solid. And tests are that solid ground that allow us to not slip back and always move forward quickly. Obviously, tests help us to make better code because it allows us the confidence to break things, and it gives us the courage to potentially refactor things in a very major way. Obviously, tests help us to make better systems because we catch the bugs earlier and we can fail faster. But a little bit more detail here. So Microsoft did a survey back a couple of years ago about what do developers do every day, and it is not, if we do it, we kind of know, but like it's non-intuitive from the outside. So it is 75% of the time these developers that Microsoft surveyed spend reading existing code. 20% of the time, rather, they spend modifying existing code, and only 5% of the time are they writing new code. One of the things that I like to say is tests are helping us with all of these things, but it's super obvious how they help with the top two, right? Reading existing code, well, tests are executable documentation that tell us how the code should be used and how it behaves. Modifying existing code, well, that's the obvious part, right? So when I make modifications, the tests help me make sure that I haven't broken anything. But actually, it also helps us writing new code as well, because tests help us to make better designs by when it is easier for me to test, that is the same as saying the code that I wrote is more modular, it has better separation of concerns, it's more encapsulated. Like those things are triple equal in mathematics, like equivalent to each other. Michael Feathers has this wonderful observation that there's a really deep synergy between testability and good design, and that, like what I was saying, all the pain that we feel when we write unit tests are telling us that we have a design problem, that we need to potentially relook at our design to make it simpler and more modular. And in my experience in the industry, Stitch Fix was the place where we did test-driven development, automated testing really well. That was something that people put in at the beginning of the company and kept going forward. And that investment was so valuable. So when I was there, and I was there for several years. We actually quintupled the size of the engineering team, went public. So, a lot of stuff happened while I was there. And for most of that time, we basically didn't have a bug tracking system. Now, we produced many bugs, maybe even more than our fair share, right? But we had kind of inbox zero for bugs, if you see what I mean, right? So we had not accumulated this large set of bugs over time. We would find them and then we would fix them, and we would find more and we would fix them. And we didn't have to hugely step out of our regular process in order for that to happen, if that makes any sense. And if you were ever able to achieve inbox zero, like you know the feeling of like, oh, I only have to deal with this small number of emails, so that I can handle that, rather than an inbox that looks like 1,000 or 2,000 messages. I don't always do that myself, can't always achieve that myself, but when I've been able to, I know the fix, or I know the value. And so we absolutely produced bugs, but we would fix them as they came, and we absolutely had a backlog of things, but that backlog was things that we intentionally decided that we were going to build later, later phases of whatever we're doing, and that backlog also contained technical debt that we took on intentionally and are going to repay later. So the other sets of techniques here that are probably familiar to everybody is not rolling changes out all at once, but doing canary deployments where we stage the rollout, going slowly. Canary means that we're looking for something that potentially is a problem, and if we see that problem, we can roll things back. And so systems that allow us to automatically roll things out and roll things back, and automatically do that by monitoring the changes in the metrics that we care about, and if the metrics look good, we can keep going with the rollout, and if the metrics don't look good, then we can pause and roll back. And the idea here is we want to make sure that deployments that we make are routine and boring. The more boring we can make deployments, the better off we're going to be. The next idea, again familiar to everybody now, thank goodness, is feature flags. So, the idea here is, where canary deployments is about successively rolling out to parts of the infrastructure a particular change, feature flags is the orthogonal idea of successively rolling out a new feature to different users or different user segments, right? And interestingly, historically, this idea of feature flags was actually independently discovered by a whole bunch of different companies about 20 years ago. Just all of a sudden, with the web, everybody needed this thing, and eBay and Google and Facebook and Yahoo all discovered essentially the same technique all at the same time. And again, this allows us to build and maintain a lot more solid systems, right? So it allows us, super importantly, to decouple feature delivery from code delivery. So we can roll out new code in a very, in that canary way, in a very progressive and controlled way, and then we can roll it out with the feature off. So now we know that all the old stuff worked, and then we can flip the feature on really easily, successively for new users, and then we can go forward and back really quickly without rolling more code. So rapidly allows us to turn on and off, as we well know. For experimentation, it allows us to separate experiment groups from control groups. And then really importantly, it allows us to develop and test and verify new code in production and do that really safely, because we can show the new stuff only to a very small number of people behind the feature flag. If we put all those ideas together, what we're doing here is essentially continuous delivery, right? So we want to be deploying services multiple times a day, which allows us to build a lot more solid systems. So we can release smaller, simpler units of work. Simplicity, again, the idea here. Smaller changes to roll back and roll forward. It's easy to understand, easy to diagnose what's going on. And one of the things that I'm proud of is that when I was most recently at eBay a couple of years ago, I helped to lead this initiative that rolled continuous delivery out to the whole company, and we were able to get huge amounts of improvement. So we actually were able to double the productivity of the engineering teams we worked with simply by working with those teams, figuring out what was slowing them down in their software delivery process, and figuring out how to move forward. And we used people are probably familiar with the accelerate metrics or the DORA metrics, deployment frequency and lead time, and we were able to make some really significant improvements in those things. And why did we do it? I was chief architect, and the reason why I spent a lot of my time working on continuous delivery was not because there weren't architectural things to change. It was because there were architectural things that needed to change, but we needed to get into this cadence of being able to reliably and repeatably release small changes to the software in order to make large-scale architectural changes. Okay. Let's put it all together in some examples. The first, I guess, architectural idea I would give is, in my view, in a large-scale system, for any given piece of data, we should have one and only one service that owns that data, right? There should be one and only one place that owns user information, that owns payment information, that owns whatever, item information or something like that. Every one of those things I mentioned is used by lots of different other parts of the system, but every one of those places that it's used is, every one of those copies of that user information or that item information or that payment information is a read-only, non-authoritative cache, and I'm using those words super explicitly. It's read-only, meaning I should never be able to modify user information in some other place that's not, the user service or whatever owns it, and it's non-authoritative, meaning that it's possible, it's legit that it's a little bit stale. It's legit that I might have made changes to the user in the central area, and those changes might have taken a little bit of time to propagate. So in a service ecosystem, we need to deal with this kind of shared data. And so one option is just synchronously calling and finding and asking the service what's the current situation. And there's nothing wrong with this technique, right? So in this particular example, we want to ship something to somebody. So the fulfillment service is calling the customer service and asking what's the customer's address. Sometimes we want the fulfillment service to be able to operate without the customer service, or maybe if we're constantly asking the customer service, that's too much load. We have lots of operational reasons maybe why we might want to move to another technique, which is an asynchronous event and a local cache. So here, the customer service still is the system of record for the customer data. It produces a set of events. In this example, it would produce an address updated event or something like that, and then that could be cached in the fulfillment service and used subsequently to send, to ship things to the customer. So joins are a similar idea. So we want, the join idea, just like a join in the database, is we want to combine information that's logically owned by one service or one domain with data that's owned logically by another service or another domain. One option, which is every web page in the world, is simply call call both sides and join it in the client, essentially, right? So in this example, we go to the customer, we want to show the order history for a customer. We go to the customer to find the customer information. We go to the order service to find all the orders for that customer. Super straightforward. Again, this is every web page in the world. Sometimes that is not enough for various reasons. So the technique there is that we would have another service as part of our ecosystem whose job it is to materialize the view, is to maintain that join between in this example, the customer information and the order information. And typically how that's done is the customer service is producing events when things about the customer changes. The order service is producing events when there are new orders that are added or updated or whatever. And then we maintain that information in this joined way. Okay. So just to finish up, I want to show two examples of where we use these kind of shared data join idea and also that inverting from synchronous calls into asynchronous stuff. So the first example, which comes from an excellent article on InfoQ and an article and a talk at the QCon conference in 2001. So it's Netflix viewing history. So the context for this thing is viewing history needs to store and process all the playback data that Netflix customers are producing, and they produce about 1 million requests per second of this data. So that's a decent amount, but that's used for lots of different things at Netflix, like viewing history, personalization, recommendations, analytics. There are tons and tons of uses for this particular data at Netflix. The original architecture here was actually synchronous. So I know, people's eyes like, what? So all the way from your browser into the web server, all the way through to persistent storage, which was then later read by the other use cases. Originally, it was synchronous all the way down. As you can imagine, that works great when it works great, but is a challenge when there's jitter in the system or really anything from an operational perspective. So there was availability and data loss when things were going well. So they re-architected it in the way that we talked about. So instead of having it a chain of synchronous calls down, think of it as an asynchronous collection of data inverted. So instead of writing all the way to the persistent storage, the receiver of that data on the Netflix side is writing to a durable queue. There's an async pipeline then to process that data, to enrich it, to aggregate it, et cetera. And then all the use cases from the other parts of Netflix are materialized views that allow those things to serve the reads. So, and you can imagine that simplified substantially the operational requirements, the resource requirements, and also could give a lot better uptime to both sides of the equation, right? Both on the write side and on the read side. And then this other example is a really wonderful one. So it comes from a talk by Scott Havens, who used to work at Walmart in 2019. So it's about the Walmart item availability service. Okay, what does item availability do? It answers the question, is this particular item available to ship to this particular customer? And so Walmart is competing with lots of other e-commerce retailers, as you can imagine, so they need to have a customer SLO of 99.98% uptime in 300 milliseconds. So they want that answer to the customer in 300 milliseconds. Are we able to ship this item to you and your location? Or more precisely, when can we get you the item that you want to order? And the original implementation was, well, it is true in either case that there is a lot of complex logic associated with whether items are available, right? What things are in inventory, what things have been reserved, what things are back ordered, what things are eligible to be shipped to particular locations or in particular cities or countries. There are sales, like when they sell stuff like a Nintendo or whatever, they put sales caps, only 200,000 can be sold. Like, there are lots of really complex things that are a part of this. So the original architecture, which Scott worked to replace, was a graph of 23 nested synchronous calls. I'm going to show his architecture diagram on the next slide. Any one of those 23, if it fails, is going to invalidate the results. And if you want to meet that 99.98 uptime in 300 milliseconds, it means that every one of those services have to have 5 nines of availability and 50 milliseconds of incremental latency at maximum for any of those individual services. So they did that. Like, this system operated, but it was super expensive to build and operate it. So it looked like this. And you don't read, the details aren't important, but like there's a lot of red, and the red shows the hot path of simply what do we need to do at runtime to answer that user's question. Okay. I'll share the slides if you really want to look at it. So instead what they did is they inverted each service to use asynchronous events. So it was an event-driven data flow, idempotent processing for the subsequent services. Every one of those services maintained an event-sourced immutable log and materialized the views of the things that it was aggregating for those other dependencies. So with this asynchronous re-architecture, instead of 23 services in the hot path, there were 2. And the asynchronous service SLOs didn't need 5 nines of availability, they only needed 3 nines, and the latency could be seconds or minutes, because again, they're only making changes not when the user's requesting them, but when the inventory changes, or when the rules change. So it was way more resistant, orders of magnitude more resilient to delays and outages, orders of magnitude simpler to build and operate. And again, this is his diagram, which he should be very proud of. So it used to be that 23 thing. Now it's Walmart.com, calls essentially a data source that stores the item availability, or rather calls that API, which goes to a data store that has served all those things. So, I mean, I'm super impressed and wish I were part of this system, because it's amazing, and everybody involved should be really proud. So thank you. So what we talked about was simple components, we talked about simple interactions, we talked about simple changes, and we put it all together with some architectural examples. So have a great conference, and I'll see you later. Thank you.